afternoon, everybody. It's 12 o'clock, so we're going to get started. I don't think I have any reminders for anybody about labs or anything like that. Does anybody have any questions? No? Okay, so we're good to jump in and get started. Last day, we found our equations for standing waves on strings. We said when we had standing waves on strings, we had to have a node at either end. Those were our boundary conditions. We thought about that. We looked at what happened as we changed the frequencies. We got a set of standing waves. We found the allowable wavelengths, allowable frequencies, and defined the harmonic number. We got into sound waves. We talked about sound waves being a longitudinal wave in air. It's a wave in air pressure, so we talked about that last time. We said that the speed of a sound wave in air depends on the temperature. There's the equation to calculate it. At the end of our class, we said if the conditions are just right, we can get a standing sound wave, just like we get a standing wave on a string. The way you know you have a standing sound wave is that it sounds loud, just like the standing wave on your string gets a big amplitude. So today we'll start with finding the expression for the wavelengths and frequencies of the standing sound waves in columns of air. So we're going to follow along the method that we did for our waves on strings. We'll apply that to sound waves in a column of air, and we'll get our expression for it. So we might be able to get through this a little bit more quickly than we did the standing waves on a string, just because the method is going to be a little familiar with us now. So our approach is, let's find the standing waves in a tube. This implies that the tube is filled with air. It has length L. We can put that on our picture if we wish. And it says that the tube is closed at both ends. If you look closely at this picture, you see that the two ends are grayed out. That's how you indicate a closed end. You shade it in. So that part is important. You can also always define it in words. Okay, so you can write closed, or you can shade it in to show closed. Assume the tube is filled with air, and we'll write that the speed of sound in air is v. The boundary conditions are, so before we can start drawing the waves, we have to know what happens at the ends. We have a closed end. Things we know about the closed end is that the molecules, which are up against the closed end, can't move, right? They're pushed up against that end. They are not allowed to move at all. So we have to have a displacement node. We know that the pressure is out of phase with the displacement pictures. If we think about the pressure, those molecules are squished up against the end. They have a higher pressure relative to equilibrium. So the pressure goes through a large change. That means we have a pressure antinode. So where we have a displacement node, we get a pressure antinode. So those are our boundary conditions. When we have the standing wave on a string, we drew the wave on a string because it was the logical thing to do. When we have standing sound waves, there are two ways we can talk about the wave. Either the motion of the air molecules, the displacement, or the pressure of the air, the pressure. So we have two choices in what kind of waves to draw. We can draw the pressure waves or the displacement waves. For our derivation here, I'm going to draw both of them. When we do problems and examples, you only have to draw one of them. You just have to be clear about which you're drawing. So in this set of tubes here, I'm going to draw the pressure waves. Make sure you always label those clearly so that I know that you know what the boundary conditions are. So let's draw our pressure waves. Let's relate the wavelength to the length of the tube. Let's use the wavelength to find the frequency, and let's find our general conditions. So for a pressure wave, we have to have an antinode at each end. So I'm going to say in my wave, this side is on a crest. The other side is also an antinode. To get my simplest wave, the other side is going to be a trough. So I'm going to go from crest to trough. In between any two antinodes has to be a node. So this is what our standing wave in the tube looks like, the simplest one. So simplest is to go antinode to antinode. I'm going to look at this fraction of a wave in the tube. The wave goes from crest to trough. So what fraction of a wavelength is this one? Sometimes it's a little tangly, isn't it? If you're not quite sure, what you could do is draw what one wavelength looks like. Typically you would draw this. My goodness, that's tiny, isn't it? Typically you would draw this, and then you would draw the other half. We're going from a crest to a trough. That is half the wavelength. Okay, so from crest to trough, antinode to antinode, that's one half of a wavelength. So in this tube right here, one half of the wavelength, this is my first wavelength, I'm going to call that lambda 1, that's equal to the length of the tube. So lambda 1 is equal to 2 times L. To find my frequency, frequency is speed divided by wavelength. So my first frequency is the speed divided by the first wavelength, V over 2L. Because this is my first wavelength, this is the simplest. This wave is called the fundamental. So we had a fundamental with waves on strings. We also have a fundamental with waves on tubes. So this one is the fundamental. Okay, next picture we draw, we have to have an antinode at each end. So I've got to have antinodes here in my pressure. I want to get more of the wave in a tube, so I have to put in another antinode. So I'll put an antinode in here. Between the antinodes are nodes. So my next wave is going to look like this. I go crest, trough, crest, and then the other half looks like this. So I go from crest back to another crest. For this wavelength, this is one full wavelength in the tube. Everybody okay with that? Crest to trough to crest, where it starts back to where it started. So lambda 2 is equal to L. Frequency 2 is V over lambda 2 equals V over L. Okay, I'm going to draw one more. Okay, this had one antinode in the middle. To get more of a wave in, I need to pop in another antinode. My nodes between my antinodes, and my wave will look more or less like this. So next I ask how many wavelengths are in this tube. I go from a crest back to a crest. That's a full wavelength. Down to a trough. That's another half of a wavelength. There are 1.5 wavelengths in this tube. So my third wavelength here is 3 divided by 2L. And my third frequency is V over that wavelength equals 2V over 3L. Everybody okay with this so far? We'd like to establish the general pattern. So let's see what our general pattern is. So in general, so lambda 1 is 2L. That could also be written as 2L divided by 1. F1 is V over 2L. That could be 1 times V over 2L. My lambda 2 is just L. That could be 2L over 2. And my frequency could be 2V over 2L. My third wavelength and frequency are okay the way they are. So for my wavelengths, I've got 2L divided by 1, 2L divided by 2, 2L divided by 3. Oh, I goofed this last one, I'm sorry. So 3 over 2 times lambda 3 is L. That means that lambda 3 is 2L over 3. Okay, sorry about that. If you catch me doing those sort of things in class, please do point it out. It just means I made a mistake writing it down. I am human and do make mistakes, probably more than once in a while. So I've got 2L over 1, 2L over 2, 2L over 3. So my general relationship is that my wavelengths, lambda n, are 2L over n. Like my waves on strings, n equals 1, 2, 3, and so on. Those are called the harmonic numbers. My frequencies, Fn, are 1V over 2L, 2V over 2L, 3V over 2L. So my frequencies are N times V over 2L. You might notice that V over 2L is my fundamental frequency, so you can also say your frequencies are N times your fundamental. Okay, where N is the harmonic number from above. Okay, questions about this pattern? So we got this by doing the pressure waves. I said last time that for your waves on the strings, your N value was equal to your number of antinodes. Notice here that that's not true anymore. I've got 2 antinodes when N is equal to 1. So that's why I caution against using any sort of these tricks to remember what your harmonic number is. You just got to look at the wave and be able to see which node you're in. So this was our pressure wave. We also could have drawn displacement waves. And I'm going to do these a little bit more quickly. In our displacement waves, we have to have nodes at either end. So I'll draw a node at the 2 ends because the air molecules can't move. To get the fundamental, I connect the 2 nodes. This is a half of a wavelength. So just like for my pressure wave, a half of lambda 1 equals L. To get my next picture, I put in another node. This time I've got a full wavelength. And to get my next one, I put in another node, another half of a wavelength. And 3 over 2 lambda 3 equals L. So we get the same results. So the derivation could have been done with the pressure waves or the displacement waves. They give the same answer, you just have different boundary conditions. Okay, questions to here? Like the standing waves on a string, these kind of have different names. Sometimes they're called the modes, the harmonics, the resonances, the resonant modes, or the different harmonics. Sometimes they're called the overtones. Because those words can get a little bit tangly, I'll always try and be very clear in what I'm asking you for. I'll probably, like if I want you to draw the third one, and sometimes they label them really tricky, rather than say draw the third harmonic, I'll say draw the N equals 3 harmonic. So I'll always try and be really specific. Your book could be a little bit less specific, so just read carefully as you go. One more thing we'll point out before we leave this slide, because this is going to be helpful. Let's take a look at what happens with consecutive frequencies. So we'll notice something about the consecutive frequencies. 2 consecutive frequencies, if I subtract them, I'll get the difference between the frequencies. So delta F is going to be some frequency N, subtract the one before it. So this might be, say, F4 minus F3, F10 minus F9, F2 minus F1. So one frequency, subtract the one before it. The nth frequency is N times F1. The N minus 1 frequency is N minus 1 times F1. So that's NF1 minus NF1 plus F1 equals F1. So delta F is equal to F1 for tubes that are closed at both ends. Okay, this is going to be a useful relationship for us, so we'll toss this in here. And closed, that's just a shorthand way of writing 4 tubes which are closed at both ends. Okay, any questions here? So that was a lot of work on one slide. Push this over to the side. The next slide in the notes, if people have printed them off and downloaded it, this one is called homework, and it's repeating the process. We just worked on tubes that were closed at both ends. For the homework, we're going to look at tubes which are open at both ends. There is a difference in the boundary conditions, so I'll just point those out even though you might have an idea already. So the boundary conditions, our tubes are open at both ends, so the ends are not shaded in, they're just clear. if they're open at both ends, we can think about what's happening with the pressure. So at the open end of the tube, like your uncapped water bottle, the air just inside the center of the tube, or just inside the opening, so the air right there inside the opening is at equilibrium with the air in the room. So at the opening, the pressure is at equilibrium. When it's at equilibrium, that means it's a node. So pressure at equilibrium, therefore we have a pressure node at an open end. For the displacement, if we think about the motion of the air molecules at the open end, right here at the opening, these air molecules are free to vibrate in and out. They can move in and out of the bottle without anything in the way. So the displacement of the air molecules, they are free to move. So they move around a lot. That is an antinode. Okay, so there are your boundary conditions for your tube, which is open at both ends. That's the boundary conditions of an open tube. So that'll be the hint to get you going on the homework. I will post the answers so that you can check if you wish as you go through. Okay, next we'll do the combination model. So let's have a tube that has length L. So we'll put our length on here. It is open at one end. That is the unshaded end. So I'll label that one open just so there's no confusion. And it's closed at the other end. That's the shaded in end. Assume the tube is filled with air and the speed of sound is v. So we want to find the standing waves. We're going to apply the boundary conditions. We're going to draw the waves, relate them to a wavelength, find the pattern for the wavelength and the pattern for the frequency. So we're going to do the same thing again. So here I've just written down the boundary conditions. At the open end, we have a pressure node because pressure is at equilibrium. Displacement antinode because the molecules are free to move in and out. At the closed end, the molecules are squished up. That's a pressure antinode. The molecules can't move. That's a displacement node. Okay, so there's the boundary conditions. I'm going to start by drawing the pressure waves. It doesn't matter if you started by drawing the displacement waves. We'll still get the same answers. So I'm going to put in my boundary condition. At the closed end, I have a pressure antinode. So let's say a crest. At the open end, I have a pressure node. I have to go from antinode to node, crest to equilibrium. So my first wave, again, this is the first one. This is the fundamental. Our next step is let's relate the amount of this wave to the length of the tube. So what fraction of a wavelength is this to go from a crest to the equilibrium?
Quarter.
That's a quarter of a wavelength. Everybody was right on top of that. That's great. So for people who were having trouble with it, we'll just draw that wavelength again. There's one full wavelength. We're going from a crest to an equilibrium. That's 1/4 of the full wavelength. Okay, so for anybody who had trouble seeing that. So 1/4 of the wavelength is equal to the length of the tube. That means lambda is equal to 4 times L. My frequency of this mode of the fundamental is V over the wavelength, V over 4L. Good there? Okay, my next wavelength, my next tube picture, I've got to have a pressure antinode, a pressure node here, and I have to squeeze in more wavelength, so I'm going to squeeze in another node and another antinode. And this is what our next wave looks like. So if we look at this one, I've got a 1/4 of a wavelength here, I've got a 1/2 of a wavelength here, so this gives me 3/4 of a wavelength. That means lambda equals 4L divided by 3. My frequency is the speed divided by the wavelength, 3V over 4L. Okay, I'll do one more wave in the tube. So I've got to have my antinode at the closed end, my node at the open end. I've got to squeeze in another half of a wavelength, about like this. So now what I've got is a full wavelength here, a quarter of a wavelength here. So in this tube I have 1 1/4 wavelengths, or 5/4 wavelengths. So that means lambda is equal to 4L divided by 5. My frequency is V over lambda equals 5 times V over 4L. Everybody good to hear? Let's write down our general relationship here. And maybe you caught on to the fact that I didn't number my wavelengths this time. I don't know if you noticed that or not. Last time I did them 1, 2, 3. I didn't do that this time, and that was on purpose. So if I look at my pattern, I've got 4L, 4L over 3, 4L over 5. So it still follows a pattern. Lambda n equals 4 times L divided by n. But this time the n's are different. N's are the odd integers only. And they're still called the harmonic numbers. So when we number these standing waves, they have the odd numbers. This is lambda 1, this is F1, the fundamental. The next one is lambda 3 and F3. Next one is lambda 5, and this one is F5. Here's where the naming of them gets really weird. Sometimes books will call this the fundamental first harmonic, third harmonic. Sometimes it's fundamental first, second harmonic. Sometimes it's first, second, third harmonic, first, third, fifth harmonic, fundamental first overtone. So that's why I'll probably always give you the harmonic number, because that's a nightmare to remember all that different wording. So read your books with caution. Make sure you know which one it's talking about when you're getting it out of the textbook. For my frequency, I get a pattern in my frequency. 4V over 4L, 3V over 4L, and 5V over 4L. So Fn is n times V over 4L. We had a question about this before. It was, they saw an equation that was V over 4L. This is where the 4L comes in. It's this kind of tube. It's also Fn is the n value times the fundamental, so that's still true. Often this is called the set of odd harmonics. So we could have done this with our displacement waves as well. I'll go through those pictures kind of quickly in case you want to see them. We get exactly the same pattern and the same results, just a different boundary condition. So it's like they're opposite. So for the displacement, we go from a node at the closed end to an antinode at the open. There's our fundamental. Our next wave has another half of a wavelength in there. And then our last one we'll draw has got another half of a wavelength. And again, we get the same pattern here. On our last slide, we calculated the difference between two consecutive frequencies. We'll do that here as well, because that is going to be a really useful tool for us. So the difference between our consecutive frequencies, so we'll give that a notice like we did on the last slide. Delta F, got to be careful with our n's here. So it's going to be some frequency Fn. Subtract the one before it, but you notice they go down by twos. So it's the 7th minus the 5th, the 3rd minus the 1st, or whatever. So it's Fn subtract f of n minus 2. So the n's go down by 2 every time. So that's n times the fundamental, subtract n minus 2 times the fundamental, nf1 minus nf1 plus 2f1. So for tubes that are open at one end and closed at the other, the change in frequencies is twice the fundamental. So if you've got one end open, one end closed, then those frequencies will change by double the fundamental. Okay, questions? I think it was last class or the one before, I said think about what if you hold up a ruler and you shake it at one end. You might notice it follows this pattern here. Okay, so this can be a guide if you were trying to work out that ruler problem. So let's do an example. So in our example, an organ tube has successive harmonic frequencies at 786 and 1310. That they're successive means there are no standing waves between these two frequencies. This is one frequency and this is the next one. Speed of sound in air is 343 meters per second. Find the fundamental. So you might notice here, we don't know which frequencies these are, right? We don't know that one of them is the fundamental or not. Yep.
How do you know standing wave between them for different frequencies? Is it one on top of the other?
Oh, that's such a good question. I was going to talk about it mostly when we get to music. When you have waves in tubes, just like waves on strings, you don't ever just have one standing wave at a time. You get a bunch of standing waves in the tube at the same time. And you can measure what those are, and if we get time today, we're going to do it today. Otherwise, we're going to do it in Friday's class. So we can show that there are many waves at the one time.
Oh.
So a tube has a whole bunch of these standing waves, and these are two of the frequencies of the standing waves that we can measure.
So the one that appears to be just one is actually made of a bunch?
Yeah, waves in tubes and waves on strings are generally not one wave. They're a whole whack of waves added together.
Okay.
Yeah.
Nice.
Okay, part A, find the fundamental frequency of the organ. There are different ways to go at this. I'm going to show you my way, and then if you have an alternative method, that's fine. You don't have to follow my way, as long as your way also makes sense. So I know that two of the frequencies I have, two successive frequencies, are 1310 hertz and 786 hertz. If I subtract those two, I'll get my delta F. So 1310 minus 786 gives me 524 hertz. Okay, so I subtract them, I know what they're different by. The frequencies always increase or decrease by the same amount. So the next lower frequency under 786 is 786 minus 524. So my next lower frequency is 262. Because it has to go down by the same amount. To get my next lower frequency, I would subtract 524 again. That would give me a negative answer. Is that sensible? No, negative frequency doesn't mean anything. That makes this the lowest allowed frequency. That makes this one the fundamental. Okay, so they all have to be separated by the same amount. You can just count it down until you get to the lowest positive number. That's your fundamental. Part B. Is your organ open at both ends or open at one end and closed at the other? Some people just answer this and say that's because an organ has to be. So they say right off the bat that an organ has to be either this or that. That's not true. Organ pipes come in different forms. Some of them are open at both ends and some of them are open at one and closed at the other. So the truth is we don't know what it's going to be until we figure it out. So to figure it out, let's think about those conditions we wrote down on our last two slides. If it's open at both sides, I'll say OO for open, open. I know that delta F equals the fundamental. If it's open at one end and closed at the other, I know that delta F is twice the fundamental. Okay, so that's a relationship that we know. For our problem, so we have Delta F is 524. That's double 262. We have delta F as 2F1, therefore our pipe is open closed. Okay, so you got to figure it out. What harmonic number corresponds to the frequency of 786 hertz? Well, we can just number them if we wish. There are different ways to do it. So the frequencies we have are 262 hertz. That's my fundamental, that's n equals 1. 786 is the next higher. It's open closed, so this must be n equals 3. The next higher is 1310. Goes up by 2, that one is n equals 5. So our answer is n equals 3. So the harmonic number of the 786 hertz frequency is 3. And for our last part, find the length of the organ pipe. Part D, we know that Fn equals n times V over 4L. So I can pick any frequency and put in the corresponding n. I know my V and I can calculate my L. I'm going to use my fundamental frequency just because I can. So F1 equals V over 4L. L equals V over 4 times F, 343 meters per second. Divided by 4 times the fundamental 262 hertz, gives me a length of 0.328 meters. So about 32 centimeters, which would be the length of one of the smaller organ pipes. Okay, any questions? Okay, so now let's do kind of a neat biological application. People get caught up on the notes first. Looks like we're good. So one open and closed tube that we have, that we use for hearing, is just the ear canal. So in your ear canal, you've got one end that's open to the atmosphere. So that's an open end. The closed end is where your eardrum is. There's air inside your ear canal. So you can get standing waves inside your ear canal. You can draw the waves if you want. If I draw a pressure wave, I go from a node to an antinode. Here's a pressure wave of the fundamental in your ear canal. The question asks, what harmonics happen in the ear canal? So right off the bat, we see that we have open closed. We know we're talking about the odd harmonics. So let's see if we can figure out what harmonics we're going to get in our ears. So my first wave in my ear is going to be V over 4L equals. Okay, what do we think about V? Should we just use 343? Kind of a trick question. Not many people's heads are sitting at a temperature of 20 degrees, right? So your head is at body temperature. So your ear canal has a temperature of body temperature. So we've got to calculate the speed inside your ear canal. So V is equal to 331 meters per second divided by the square root of temperature, about 37 in most humans. Some people are a little warmer, some people are a little colder, but the average human is about 37 plus 273 divided by 273 equals 353 meters per second. So the speed is a little bit higher because it's warmer. So that's our V. What about our L? Most humans have about the same size. Most adult humans, babies are probably a bit smaller. Most adult humans have an ear canal that's a length of about 2.5 centimeters, about an inch long. Okay, again, humans will vary a little bit, but not by tons. Put those numbers in, we get the first frequency at 3,530 hertz. So that's the first standing wave frequency that you can get in your ear. The next one would be F3 equals 3 times F1 or 3 times V over 4L. That's 10,600 hertz. We can draw that one if we wish. would look like that. And then the next one, F5, is 5 times F1, 17,700 hertz. We can draw that one too if we want. If we went any higher, we would get to 7 times F1. That would exceed what most humans can hear. Most humans can only hear up to about 20,000 hertz. Some people can go a little higher. As you age, you're going to go a little bit lower. I probably can't hear this one. I can't hear that high. So what does it kind of mean biologically? So I'm going to switch to a sound generator. If you're looking to do one just to play with a little bit at home, there's the web address of the one I like the best. So what I'm going to do is I'm going to play a tone, and I want you to notice how it feels when we get to these frequencies. What does that seem like to your ears? As we get, oh sorry, I'm pointing at the sheets on the page. So 3,500, 10,000, and 17,000 or 18,000, notice what that feels like. As we get to the higher frequencies, it is going to sound kind of sharp. So if you kind of are hearing sensitive, feel free to cover your ears or to step out. So if this is going to bother you, you're welcome to not play. So I'm going to play the tone. Right now it's playing at 7 hertz. Most humans can't hear as low as 7 hertz, so we'll come up. People can more or less hear it now. We're at 30 hertz. I think I can turn it up a little bit. It's going to get sharp quickly, so feel free to cover your ears if you want to. And the first frequency we're going to look at for what it feels like is around 3,500. Okay, next one is 10,000. And then the next one is 17,000. I can't hear it at all anymore. Probably a lot of you can still hear it. I can't hear it at all. Okay, so now I'll turn it off. So what happens is, and let's remember what a standing wave in an air column is. When you blow across your pop bottle, you'll get certain frequencies ring really loud. In our ear canals, we're going to get these 3 frequencies at standing waves. These feel louder. So if you put humans in sound experiments and you play these particular frequencies, people will be, holy cow, that's loud, right? Even if you haven't turned up the volume, just because it's a standing wave. So humans will mark that as a very loud volume because they're getting the standing wave in the ear. Okay, so that's a crossover to biology. Let's do another example. So in this example, we have a tube with length 50 centimeters. So L equals 0.50 meters. It's capped at both ends, so this is closed. We get standing waves by tapping on one end. This is something like you're going to do in your lab next week. We know the speed of sound in air. That's going to be the first bit we do. And we know the speed of sound in helium. That's going to be the second bit we do. Part A, find the frequencies of the first 3 harmonics in the tube. So part A, if it's closed at both ends, we know that Fn is n times v over 2L, where n is 1, 2, 3, and so on. F1 is v over 2L. So our first 3, we've got air, so that's v of air. 344 meters per second divided by 2 times 0.500 meters equals 344 hertz. Next frequency is F2, that's twice F1, equals 688 hertz. Next one, F3, is 3 times F1, or 1,032 hertz. Okay, so that's the frequencies of the standing waves in air. We could then fill the tube up with helium and ask about those frequencies. And that's an experiment we used to do in Physics 1051 before we kind of got this global helium shortage, so we don't do that anymore. So if we were in helium instead, Fn equals n times V of helium divided by 2L. So F1 is V of helium divided by 2L, 999 meters per second divided by 2 times 0.500 hertz equals 999 hertz. F2 is 2 times F1, 1998 hertz. F3 is 3 times F1, 2997 hertz. Part C I'll leave for homework. Find the wavelength of each of those frequencies and draw the standing waves in the tubes. So find the wavelengths for those bits. Okay, questions to here? And those are kind of standard problems. There's not a lot of different stuff I could ask here. Okay, so now we're going to come back around to the question we had earlier about the waves in the tubes. And it's kind of an application of standing waves. We're just going to talk about music for a moment. So I've got a couple of apps on my phone. I'll zoom in a little bit. The two apps I have that I use that I really like, it's the oscilloscope app and the FFT app. These are available for free for Androids and for iPhones, so feel free to download these and play with them if you wish. What the oscilloscope does is it takes any sound wave and shows it, oh my goodness, and shows it as a sine wave, so it shows what the pressure wave looks like. What the FFT app does, if I can find it, oh, I'm so bad at phone, I'm sorry. What this app does, so the last app showed that sound is a sine wave. We know that sine waves have well-defined periods and frequencies. This one shows the frequencies present. We're going to be doing this in the lab as well. So this is showing the frequencies present in my voice right now. When we have music, and first two examples, I guess everybody's heard these two things before, like a banjo versus a cello. So they're fundamentally the same instrument. They're strings on a body, but they sound really different, right? Banjo is kind of plucky and a cello is really deep and rich. The next two instruments, I'm going to do my best to play them. I am not musical, so kindly forgive me. It's not going to sound nearly as well as you all can do. The two instruments I got for my kids, I got the recorder. I think a lot of Canadians learned to play this in like grade 5. So if you went to high school here in Newfoundland, you probably did learn how to play this. I'm going to play a C note on the recorder. So my kids were showing me how to do this last night. When I play the C note, it should show the frequency on the FFT here. Okay, so that main spike was the note of this recorder. A couple of things you might have noticed is that there's one main spike, so that's one thing, there's one frequency. And the second thing you might notice is it doesn't actually sound all that nice. Okay, so you blow a little bit on the recorder. It's not really that great. Part is me, part is the recorder. Okay, next I have a flute. People who have heard flutes before, not played by me, recognize that a flute probably sounds a little bit more than a recorder. It's a little bit richer and fuller. So I'm going to try playing the C note on the flute. Couple of things to notice there. First of all is the number of frequencies present. Okay, hopefully that's good enough. There was a few extra peaks, and it sounded at least marginally better than the recorder. So in these wood instruments, same as with the string instruments, when you have more resonant frequencies present, it sounds better, right? The more standing waves gives a nicer sound. Same thing happens kind of with singing, if I choose to embarrass myself a little further. I'm gonna try and whistle.